They called it the slowest engine GM ever made. Critics laughed at its pathetic horsepower numbers. Car magazines ignored it completely. But this diesel power plant would quietly outlast, outwork, and economically destroy every gasoline V8 that Detroit's muscle car era ever produced. While Corvettes and Camaros were burning themselves out chasing quarter-mile times, this forgotten workhorse was racking up million-mile odometer readings without breaking a sweat. And picture this. It's 1978 and you're standing in a GM dealership. The salesman is trying to convince you to buy a diesel-powered Oldsmobile. The gas-powered version makes 170 horsepower. The diesel? Just 120. The acceleration is glacial. The engine sounds like a tractor. Every car enthusiast you know is telling you you're making the biggest mistake of your life. But here's what they didn't understand, and what GM's engineers knew all along. This wasn't about winning drag races. This was about winning a completely different game. The GM diesel engine story isn't just about one motor. It's about a fundamental engineering philosophy that challenged everything the American automotive industry believed about power and performance. While Ford and Chrysler were locked in horsepower wars, GM's diesel division was quietly engineering engines that could run for 500,000 miles on regular maintenance. They were building power plants that delivered twice the fuel economy of their gasoline counterparts. They were creating torque monsters that could pull houses off their foundations while barely raising their idle speed. And to understand why GM's diesel engines became legendary among those who actually needed their vehicles to work for a living, we need to travel back to the early 1970s. The muscle car era was dying. The 1973 oil crisis had just sucker-punched the American economy. Gas prices quadrupled overnight. Suddenly, those big block V8s that Americans loved weren't just expensive to feed. They were becoming impossible to justify. Insurance rates on performance cars were astronomical. Emission regulations were strangling horsepower. The EPA was cracking down hard. And General Motors saw the writing on the wall before anyone else. While their competitors scrambled to detune their gas engines to meet emission standards, GM made a radical decision. They would adapt diesel technology, previously reserved for trucks and industrial equipment, for passenger cars. The project started in 1975 under the codename Project 77. The goal was ambitious: create a diesel engine that could fit in existing GM passenger cars, deliver 50% better fuel economy than gasoline engines, and meet all upcoming emission standards without catalytic converters. The engineering team, led by Chief Engineer Charles Ammon, faced an immediate problem. Diesel engines operate on a completely different principle than gasoline engines. A gas engine uses spark plugs to ignite a mixture of fuel and air that's been compressed to about 10.1. Simple. Predictable. Diesel engines compress air alone to ratios of 20.1 or higher, so much pressure that the air temperature hits 1,000 degrees Fahrenheit. When diesel fuel is injected into this superheated air, it ignites spontaneously, no spark plugs needed. But this extreme compression means extreme stress on every component. Here's where it gets interesting. The team couldn't just start from scratch. GM executives demanded they use as many existing production components as possible to keep costs down. So the engineers took the proven Oldsmobile 350 cubic inch V8 block and completely reimagined it. They increased the main bearing size from 2.5 inches to 3 inches. They upgraded the connecting rods from cast iron to forged steel. They designed new cylinder heads with smaller combustion chambers to achieve that crushing 22.5.1 compression ratio. The crankshaft was beefed up to handle the massive torque loads. Every internal component was overbuilt by gasoline engine standards, and the result was the Oldsmobile 350 diesel, internally designated LF9. On paper, it looked terrible next to its gasoline sibling. The gas 350 made 170 horsepower at 4,000 RPM and 275 lb-ft of torque. The diesel version, just 120 horsepower at 3,600 RPM, but that torque number, 220 lb-ft at just 1,600 RPM, told a different story. This engine made maximum twist at idle speeds. It didn't need to rev, it just pulled. The first production diesel Oldsmobiles hit showrooms in 1978. The 98, Delta 88, and custom cruiser wagons could all be ordered with the new power plant. The marketing department didn't know what to do with them. How do you sell slow in the land of the stoplight Grand Prix? GM's answer was brilliant in its simplicity. They didn't talk about performance, they talked about range. A diesel 98 could travel 600 miles on a single tank, Los Angeles to San Francisco without stopping for fuel, Chicago to Washington, D.C. on one fill-up. But the real revelation came from an unexpected source: taxi companies. Yellow Cab in New York City bought a fleet of diesel Chevrolet Impalas in 1978 for testing. These cars ran 24 hours a day, 7 days a week, in the most punishing urban environment in America. Stop-and-go traffic, potholes that could swallow a Volkswagen, drivers who treated the accelerator like an on-off switch. After 6 months, the results were staggering. The diesel cabs were averaging 26 miles per gallon in city driving. The gas versions? 11 mpg on a good day. Maintenance costs were 40% lower. The engines showed minimal wear after 100,000 miles. The secret was in the diesel's design philosophy. Gasoline engines make power by spinning fast. The classic no replacement for displacement, augmented by revs equal power. They're sprinters designed for explosive acceleration and high RPM operation. But high RPM means heat. Heat means wear. Wear means death. Diesel engines are marathoners. They make power through compression and torque multiplication. They run at lower speeds, lower temperatures, with less internal friction. Every component is overbuilt because it has to survive those massive compression forces. And attention, let me put this in perspective. A typical gasoline V8 in 1978 had pistons that traveled 2,800 feet per minute at cruise speed. The diesel? Just 2,000 feet per minute. That's 28% less distance the pistons traveled for every mile driven. Less friction, less heat, less wear. Over 200,000 miles, those pistons traveled 50,000 fewer miles inside the engine block. The math was undeniable, hence GM doubled down on diesel development. In 1979, they introduced a smaller 260 cubic inch V8 diesel for mid-size cars. In 1982, they shocked everyone with a 263 cubic inch V6 diesel that delivered 85 horsepower but an incredible 165 lb-ft of torque at just 1,600 RPM. This engine, designated LT7, became legendary in the Chevrolet S10 pickup and Blazer. It couldn't outrun a riding lawnmower, but it could pull a boat up a mountain while getting 30 miles per gallon. The technical specifications of these engines revealed GM's obsessive attention to durability. The cylinder walls were induction hardened to Rockwell 50 hardness, harder than most knife blades. The valve seats were made from stellite, a cobalt chromium alloy that could withstand temperatures that would melt ordinary steel. The fuel injection system, supplied by Stanadyne, operated at 1,800 psi, primitive by today's common rail standards, but revolutionary for passenger car applications in 1978. But here's what really separated GM's diesels from their gasoline counterparts: the torque curve. A gasoline engine's torque curve looks like a mountain. It builds gradually, peaks, then falls off. You have to hunt for the sweet spot. A diesel's torque curve is a mesa, flat, broad, and consistent across the entire operating range. The LF9 diesel made 90% of its peak torque from 1,400 to 2,800 RPM. You never had to downshift. Fourth gear would pull from 15 mph to highway speed without complaint. And this characteristic made diesel-powered cars surprisingly competent in real-world driving. Sure, a diesel Cutlass Supreme would lose every stoplight race, but from 30 to 50 mph, the speed range where most passing happens, it was only half a second slower than the gas version, and it did it without downshifting, without drama, just a steady surge of twist. Nadidena. The durability story started accumulating by 1980. A traveling salesman in Michigan put 387,000 miles on his 1978-98 diesel with nothing but oil changes and one transmission rebuild. A farmer in Nebraska used a diesel custom cruiser wagon as a farm truck, regularly pulling 6,000-pound loads. After 250,000 miles, compression was still within 5% of factory specifications. The engine had never been opened. GM's diesel engines found their perfect application in an unexpected place, motorhomes. The 403 cubic inch diesel V8, introduced in 1979, became the engine of choice for GMC motorhome conversions, making 180 horsepower and 320 lb-ft of torque. It could maintain highway speeds while pulling a 12,000-pound motorhome up a 6% grade. More importantly, it could do it all day long without overheating. Gasoline engines in the same application would overheat, detonate, or simply wear out from the constant load. Nensin, the industrial applications were even more impressive. GM's 379 cubic inch diesel V8, primarily used in medium-duty trucks, was rated for 5,000 hours of operation at maximum load. That's equivalent to driving 200,000 miles at full throttle. No gasoline engine could survive a tenth of that punishment. These engines powered generators, pumps, compressors, and agricultural equipment where reliability meant the difference between profit and bankruptcy. But let's talk about the elephant in the room, the head bolt failures that nearly killed GM's diesel program. The early LF9 engines had a fatal flaw. The head bolts were TTY, torque to yield, designed to stretch during installation for perfect clamping force. But they couldn't handle the extreme pressure spikes of diesel combustion. Head gaskets failed. Coolant mixed with oil, engines hydrolocked. The warranty claims were catastrophic, and GM's response revealed their commitment to the diesel program. They didn't abandon it. They fixed it. The 1981 engines got stronger head bolts. The 1982 models received improved head gasket design. By 1983, the DX block was introduced with thicker cylinder walls and reinforced webbing. The 1985 engines were essentially bulletproof, incorporating every lesson learned from 7 years of production. The fuel system evolution was equally dramatic. The early mechanical injection pumps were agricultural-grade simple, but lacked precision. The 1982 introduction of the DB2 rotary pump improved fuel metering by 15%. The 1984 electronic fuel control system added altitude compensation and cold start programming. By 1985, GM's diesels were starting instantly at minus 20 degrees Fahrenheit without block heaters, something their German competitors couldn't match. Here's a specification deep dive that reveals the engineering philosophy. The Oldsmobile 350 diesel's rotating assembly was 47 pounds heavier than the gasoline version. The crankshaft alone weighed 78 pounds versus 59 for the gas engine. The connecting rods were shot-peened for fatigue resistance and magna-fluxed for crack detection. Every single one. The pistons were gallery-cooled, with oil jets spraying the undersides to manage the extreme combustion temperatures. The camshaft was designed with reduced lift and duration, 0.375 inches of lift versus 0.400 for the gas engine, because diesel engines don't need aggressive valve timing. They need reliability. The economic impact was undeniable. By 1982, GM calculated that diesel buyers were saving an average of $600 per year in fuel costs, equivalent to $1,800 in today's money. Over a typical 5-year ownership period, the diesel option paid for itself twice over. Fleet operators saw even better returns. A taxi company operating 100 diesel vehicles saved $60,000 annually in fuel costs alone. But the real advantage showed up in unexpected ways. Diesel owners discovered their engines barely degraded over time. A 100,000-mile diesel still delivered 95% of its original fuel economy. A gasoline engine with the same mileage typically lost 15–20% efficiency from ring wear, carbon buildup, and valve seal deterioration. The diesel's lower operating temperature and pressurized fuel injection kept the combustion chambers clean. The torque advantage became legendary among those who actually worked their vehicles. A diesel-powered El Camino could pull a 5,000-pound trailer up a 10% grade at 55 mph. The equivalent gasoline engine would be screaming at 4,500 RPM, temperature gauge climbing toward the red. The diesel did it at 2,200 RPM, with the temperature needle rock steady in the middle. No drama, no stress, just relentless pulling power. Engineer GM's Marine Diesel division took the automotive designs and adapted them for boat use. The 6.2-liter diesel V8 became a favorite for displacement hull cruisers, where fuel economy mattered more than speed. These engines would run for 3,000 hours between overhauls, equivalent to 150,000 automotive miles. They sipped fuel at 2.5 gallons per hour while pushing 30-foot boats at hull speed. Gasoline marine engines consumed twice that. Then the military took notice. In 1982, GM won the contract to supply 6.2-liter diesel engines for the new HMNWV, the Humvee. The military didn't care about acceleration. They cared about reliability, fuel commonality with other diesel equipment, and the ability to run on JP8 jet fuel in emergencies. The naturally aspirated 6.2 made just 130 horsepower, but 240 lb-ft of torque. It could ford 30 inches of water, operate at 60-degree side slopes, and run wide-open throttle in 120-degree desert heat without failing. The 6.5-liter turbo diesel, introduced in 1992, took everything GM learned and cranked it to 11. With 180 horsepower and 360 lb-ft of torque, it finally had respectable power, but more importantly, it incorporated decades of durability improvements. Induction-hardened cylinder bores, roller camshafts, high-pressure oil-cooled pistons, electronic injection control. These engines regularly exceeded 300,000 miles in Chevrolet and GMC pickups with basic maintenance. The comparison with gasoline engines became even more stark as both technologies matured. A 1994 Chevrolet K2 500 with a 6.5 turbo diesel could tow 10,000 pounds while delivering 20 mpg highway. The big block 454 gasoline option could tow 10,500 pounds but got 10 mpg on a good day and required premium fuel. Over 100,000 miles, the diesel owner saved $15,000 in fuel costs. The diesel was still running strong at 200,000 miles when the gas engine needed a rebuild at $120,000. But here's what the horsepower-obsessed critics never understood. In applications that required constant power output, generators, pumps, compressors, welders, diesel engines absolutely dominated. A gasoline engine running at constant high load would overheat, detonate, and destroy itself in hours. A diesel would run for years. The Lower Colorado River Authority in Texas ran GM 6.5-liter diesels in their pump stations 24/7 for 5 years straight, shutting down only for oil changes. Try that with any gasoline engine. The agricultural sector became GM Diesel's biggest non-automotive market. Farmers discovered that a 6.2-liter diesel could power an irrigation pump all season long on less fuel than a gasoline V8 used in a week. The engines ran at constant 1-800 RPM for thousands of hours, never missing a beat. When John Deere and International Harvester dealers couldn't deliver engines, farmers bought wrecked GM pickups just for the motors. The Detroit Diesel Division, GM's commercial engine subsidiary, took the automotive diesel technology and scaled it up. The 8.2-liter Wanderers fuel-pinchered V8 diesel became legendary in city buses and delivery trucks, making 210 horsepower and 460 lb-ft of torque. It wasn't fast, but it would run 1,000,000 miles with proper maintenance. Transit authorities documented buses exceeding 500,000 miles without major engine work. The secret was the same as the smaller engines: low stress, over-engineering, and torque-focused design. The numbers tell the story. By 1985, GM had sold over 1.5 million diesel engines across all divisions. Customer satisfaction among commercial users exceeded 90%. The problem was perception. Consumer reports and automotive journalists focused on acceleration times and sporty handling crucified the diesel cars. They didn't understand that someone buying a diesel Oldsmobile wasn't cross-shopping a BMW. They wanted reliability, economy, and longevity. They got all three. The technical innovations GM pioneered became industry standard. The pre-combustion chamber design they developed for smooth combustion was copied by Mercedes-Benz. The hardened valve seat technology appeared in Volkswagen diesels 5 years later. The electronic injection control algorithms GM developed in 1984 formed the basis for modern common rail systems. They were decades ahead of their time. And even the failures taught valuable lessons. The head bolt crisis of 1979-1981 led to development of multi-layer steel head gaskets that could handle 3,000 psi cylinder pressures. The injection pump cavitation problems of 1983 resulted in improved fuel system designs that eliminated air intrusion. The cold start issues in northern climates drove development of intake air heaters and glow plug systems that started diesels at -40 degrees. The real vindication came from the used market. By 1990, 5 years after GM stopped selling diesel cars, used diesel Oldsmobiles and Cadillacs commanded premium prices. Buyers who understood their advantages would pay $2,000 more for a diesel Delta 88 than an equivalent gas model. They knew something the automotive press didn't. These engines were just getting broken in at 100,000 miles. Nothing sense. The commercial success was even more pronounced. GM's 6.2 and 6.5-liter diesels powered everything from airport ground support equipment to military generators to offshore oil rig pumps. Any application that required reliable, continuous power gravitated toward these engines. They weren't sexy, they weren't fast, but they absolutely refused to quit. And today, when we talk about million-mile vehicles, we're usually discussing modern diesels with advanced metallurgy and computer controls. But GM was building million-mile capable engines in 1978 with slide rules and mechanical injection. They understood something fundamental. In the real world, reliability beats horsepower, efficiency beats acceleration, and torque beats revs. The legacy lives on in unexpected ways. The Duramax diesel engine, GM's current heavy-duty offering, traces its design philosophy directly back to those maligned Oldsmobile diesels. Overbuilt internals, massive torque at low RPM, bulletproof reliability. The only difference is modern technology allows them to also make impressive horsepower. But the foundation, the idea that a diesel engine should be engineered to outlast the vehicle it powers, came from those pioneering engines of the late 1970s. The enthusiast community has finally recognized what GM achieved. Diesel Oldsmobile and Cadillac clubs preserve these vehicles. Restoration parts are being manufactured again. Young enthusiasts are turbocharging 6.2-liter diesels and making 300 horsepower while maintaining that legendary reliability. They're proving what GM engineers knew all along. These engines had massive untapped potential. So, the next time someone tells you GM's diesel experiment was a failure, remind them of this. Those once terrible diesel engines are still running today, 45 years later, with 500,000 miles on the clock. They're powering generators in Alaska, irrigation pumps in Texas, fishing boats in Louisiana. They're doing exactly what they were engineered to do, working. The muscle cars they were compared to? Most of them grenaded their engines before 100,000 miles, and when in the end, GM's diesel engines didn't outsmart gasoline engines by being faster, more powerful, or more exciting. They did it by being exactly what they were designed to be, unstoppable workhorses that prioritized function over form, efficiency over excitement, and longevity over lap times. They won the war of attrition. While gasoline engines burned bright and burned out, diesels just kept burning mile after mile, year after year, decade after decade. And that's the ultimate irony of the GM diesel story. The engines that car magazines called the worst ever made turned out to be some of the longest-lasting power plants in automotive history. They didn't win by conventional metrics. They won by redefining what winning meant. In a world obsessed with quarter-mile times, GM built engines designed to win at 250,000 miles. The lesson is clear. Sometimes the smartest engineering solution isn't the flashiest, fastest, or most powerful. Sometimes it's the one that's still running when everything else has broken. GM's diesel engines proved that there's more than one way to define performance. And for those who needed their vehicles to work for a living, not just play on weekends, GM's definition was exactly right. What do you think? Were GM's diesels ahead of their time, or was America just not ready for efficiency over power? Drop a comment below with your diesel stories. And if you enjoyed this deep dive into GM's most underrated engines, make sure to subscribe for more engineering stories that challenge everything you thought you knew about automotive history.